welcome back to the problem solving session for the Introduction to Fluid Mechanics course. I hope I am audible. Can someone please say yes or no in the chat? I hope I'm audible. Okay, so I will assume that I'm audible and okay. So as per the agenda followed by last week, I will again I will again go on with discussing the topics that were taken by Professor Chakraborty in the lectures. I'll again briefly go through them. If you have any doubt, you can ask me. And again, just for saving time, I will suggest that if I'm unable to clear some doubts from my end, you can please go back to our lectures and clarify it. So there were some doubts in the last week's discussion that was regarding the this relation where Professor Chakraborty wrote that surface S1 is equal to Sn1, S2 is equal to Sn2, and S3 is equal to Sn3. Okay, so just for saving time, I will not go back and discuss what is S1, S2, and S3. So I will just I'll just go back to the derivation directly, and then you can just clarify it. Okay, if you have any doubt even after that, I'll just suggest that you can go through the books suggested by Professor Chakraborty, and then let's hope we can handle that. Okay, so again, just to reiterate, the last week's question was how Professor Chakraborty mentioned that S1 is Sn1, S2 is Sn2, and S3 is Sn3 from this surface, where this surface was used to find the relationship between the an expression for the traction vector, which is T1 in this case. Okay, so what we do is that here surface S1 basically implies that the projection of surface S, which is this big surface, on the surface that has the normal vector in the I cap direction or the x direction from this diagram. Okay, just to again confirm from my end, if I'm audible, please someone say yes, so that you do not feel that I am not speaking anything throughout the session. Somebody can please write yes, or just gives a thumbs up in the okay, Divyanshu, thank you so much. Okay, then I think I'm audible. Then let's continue. So then so to find a projection between to find a projection of S on S1, we need to find the we need to find the projection of surface S on S1, which is this surface. Okay, so that is given by the relation S is S1 S1 cos theta. For example, if I say that the angle between the surface S and S1 is theta, then the projection of S on S1 will be S1 cos theta. Okay, you can find it out how you can do it. It's just the finding the components of the vector. So in that idea, I hope you can deduce it yourself as well. So in that, keeping that idea in mind, we can say that the projection of S on S1 would be S1 cos theta. Okay, projection of S1 would be, S1 would be S cos theta. Okay, just to clarify myself, S would be S cos theta. Then the angle between these two surfaces S and S1 will basically be the angle between their two unit vectors. Okay, between their two unit vectors, that is I cap. The normal vector to surface S1 is I cap, so it is I cap, and the normal vector to surface S is N cap, where N cap is N1 I cap plus N2 J cap plus N3 K cap. Then from definition of dot product, we can write that I dot n cap would be the magnitude of I and magnitude of n multiplied by the angle between I and n, that is theta. Cos of the angle between I and n, that is theta, that is cos theta. Now, since the magnitude of I, a magnitude of the unit vector I cap is 1, and as well as a magnitude of unit vector that is perpendicular to the surface S is 1, then magnitude of I and I cap and n cap is 1. So we can say that I dot n cap is equal to cos theta. Okay. Then since cos theta is I dot n cap, then we can replace this cos theta by uh, n1, because I cap dot n cap is n1. Okay, you can just do a cross product between I cap and n cap. You'll find that all the this uh, n2 component and n3 component will cancel out, because the corresponding components with respect to I is the vector I cap is 0. Then we'll only have I dot n cap would be n1. Okay, so we can write cos theta as n1. Then it will imply that s1 is s cos theta from this relation. Then s1 is sn1. And similarly, we can write s2 as sn2 and s3 as sn3. So that's how screen is not visible. Uh, is the screen not visible? Others, can you please say whether the screen is visible or not? Others, can you please say whether the screen is visible or not in the chat box? Chandan cannot see the screen. Can others also not see the screen? Can you please say? Others visible. Okay. Okay. Chandan, it seems that Divyanshu is able to see the screen. Can you please reconnect? I think that would be good, because others are able to see it. So there might be some technical. Yes, Divyanshu. It seems that there is some technical error from my connection. I'm not able to hear you. So I'm sorry for that. I'm still working on it. Please give me some time. Probably by next week I will be able to rectify what's happening. Okay. I didn't get any time to look into that this week. I'm sorry for that. So let us try to handle the session by uh, by continuing the class today, at least with the chat box discussion. But I'll try to rectify it by next week. Okay. Sorry for that. Okay. So I hope the doubt is clear. Other last week I guess Divyansh was also there, and there was Kannad. I think things it seems it didn't join, but I hope the doubt is clear. If someone are new, then it may seem that I'm reiterating again and again, but this is doubt that we are stuck last week. So I hope it is clear. Anyone who sees the video recording will be able to rectify and just it will feel all right. Okay. Okay then. So now let's come into the week two discussions. So this week we were Professor Chakraborty primarily focused on some fluid properties such as density and primarily density and viscosity. And what is the role of viscosity in fluid mechanics, and also I discussed some examples. So with that idea in mind, with that contents in our hand, let's briefly go through them one by one. And if you have any doubt in between, you can kindly ask. I'll try to clarify it as much as possible. Okay. So density by its very definition is given by mass per unit volume. Okay. So the expression used by Professor Jacob in the lectures was rho is equal to limit delta V tends to 0, where uh, uh, rho is delta M by delta V, where delta V tends to 0. That's the definition of density he used. He also mentioned that the choice of this delta V is again also crucial. Okay, so he mentioned that this delta V has to be equivalent to, ideally should be equivalent to delta V star, where V star is the volume corresponding to the length scale L star, where L star is equal to the mean free path of the fluid molecules in the flow. Okay, so let us take a look in this diagram. So he mentioned that this choice of delta V is again crucial, because we cannot take delta V to very small as well, because ideally you may think that as delta V tends to very small or 0, then our calculations will become more and more accurate. But that's not the case, because if the choice of delta V is less than, the volume, the length scale corresponding to the volume is less than the mean free path of the fluid, we will see that there are rapid fluctuations in its measurement. Okay, because if we look into each and every the length scale is much more than a characteristic length scale, then we will see there are rapid fluctuations in the measurement of density. Similarly, if the length scale is much greater than the mean free plot. For example, if it is much greater than the mean free part of the of the fluid flow, then you will see that again there is variation in the measurement of the density, because this choice of landscape will not be able to take into account the local variation of density that's occurring in the fluid flow. That's why the choice of this landscape is also important, and ideal choice of landscape is the characteristic landscape of the mean free path of the uh, fluid molecules. Okay, so, and this again gives us a uh, what to say, gives an idea, or gives us a taste of the application of the continuum hypothesis, because if the landscape is much smaller, then the continuum hypothesis becomes invalid. Basically, like if the land scale that we are choosing. Okay, so yeah, Divyanshu, since you can ask the question. Yeah, okay. If there's any doubt, you can ask the question. You can write in the chat box. Is that cube is that cube implies 3 dimensions in the lambda? Yes, no, not 3 dimensions actually. It is just to show a measurement of volume, because if say L is the characteristic length scale, okay, let us say LC, then the order by which the volume of that particular element will vary is LC cube, right? Like it may not be exact formula, but I'm just saying the order by which it varies is in the cube of that length scale. For example, if the characteristic length scale of your measurement is length is say 1 meter, then sorry, say 2 meter, then the volume of that particular object would vary by uh, L cube. That is, it will be in the order of 8 meter cube. So that's the idea behind that. So is it clear? Okay. Yes, so as I was mentioning that again, if the length scale that we choose is much smaller than the mean free part, so then it basically means that the continuum hypothesis is not valid. You are dealing with length scales which are smaller than a mean free part, so basically not considering the continuum hypothesis of the fluid flow. So this will cause rapid fluctuations in your measurements, and again you will not be able to measure a proper value for density. Okay. Then we come to the concept of bulk modulus. Again, we will not extensively apply the concept of bulk modulus in our study, but again it's important, because when we discuss about the Bernoulli's equation, or discuss about the derivation of the Navier-Stokes equation, then we will see how the concept of bulk modulus comes to the picture. It basically helps us to understand the incompressible nature of the fluid flow, but we will not apply it extensively in our study. So the two parameters that we will deal with again and again is the density and the viscosity, and again both of them can be clubbed together to define the kinematic viscosity, as you might have seen in lectures. But just it's again a good idea to know the concept of bulk modulus, because it helps us to understand the concept of compressibility. Okay, so the bulk modulus is defined as the ratio of the change in pressure to the ratio of the volumetric strain rate. Okay, again the negative sign is taken into account to consider the fact that this delta V is negative, and so that we need a positive value, because if we compress a fluid, then this volume will go down. So to take into account the compressibility effects, we just take a negative sign, so that our value of K becomes positive. Okay. So now we would like to find relationship between we want to express this change in density in term. Okay. Yes, Divyanshu, you can ask the question in the chat box. Actually, like You can directly write your question in the chat box, since we are having some difficulties to interact through mics. So you can directly write your question in the chat box. I will just look into it and answer it. Okay. So just to not what to say, disrupt the flow of our discussions, I will. Okay. Is that volumetric strain rate? Yes. Yes. It is volumetric strain rate. Is it okay? Change in volume by the initial volume. Is that fine? Is it fine, Divyanshu? Okay, then I think we can. Oh, okay. Okay, I just confused. There is no divide by time. Okay, but it's how volumetric strain rate. Okay. That's again a good point to discuss. So let me just look into it. Okay, then I'm sorry, this would be volumetric strain. Okay, I'm sorry. Is it fine then? It will be volumetric strain only, not strain rate. Yeah, that's a good thing to point out. Point out. Yeah, it will only volumetric strain. Okay. Thanks for pointing it out. Okay, I'm sorry for the confusion. Okay, let's proceed. So now we would like to express this change in say, since we are dealing, we would like to understand like how to take into account the effect of this bulk modulus to understand the compressibility effects. Okay, so the best parameter that we can consider to take into account this compressibility effects is density, right? Because it's a measurable quantity, so we will able to uh, see how the variation in the density can be expressed in terms of this bulk modulus. Okay, so let us look into it, how we can derive it. So we can write mass as the product of density times the volume. Then we take the natural log in both sides, so we can write ln m is equal to ln rho plus ln v. I just use v cut so that we are not confusing it with velocity. Okay, then if we take the derivative on both sides, from the conservation of mass, change in dm would be 0, so change in mass would be 0, so the right hand side will become 0, and we can write the left hand side, express the left hand side as d rho by rho plus dv by v. Okay, where v is the volume in this case. So we can write d rho by rho as the negative of dv by v. Now we know that the bulk modulus is defined as delta p by, sorry, just write it, k is delta p by negative of delta p by delta v by v. Okay, so since delta v by v is equal to minus delta rho by rho, so taking into consideration these both negative signs, we can write k as delta p by delta rho by rho, or it will be equal to rho into delta p by delta rho. So now there is again one consideration here. For most of the flows that we discuss in our course, there the pressure would vary as the kinetic energy. Okay, so again there is a concept of taking the characteristic length scales. Okay, so in fluid flows we need to know how the parameters vary. Okay, for example, as I mentioned in previous class, that for defining the Reynolds number, it is actually we need to find the characteristic length scale of the flow. For example, if this is the flow through a pipe, then the characteristic length scale is the diameter of the pipe, not the length of the pipe. That's the diameter of the pipe. Okay, so similarly, how we could say that, because we see that it is to the it is along the diameter of the pipe that we see a considerable change in the fluid properties, so we can consider the diameter of pipe as a characteristic length scale. So similarly, all other parameters such as your velocity, how the velocity varies, we again need to have a characteristic velocity scale. Okay, so similarly for pressure also we need to have some scale, like how it varies in our fluid flow. So pressure is an interesting parameter because it itself does not have any characteristic scale, but it depends on the parameter that governs the flow. Okay, so if it is a pressure grade, if I say if the flow is uh, governed by the kinetic energy of the flow, then the pressure would vary as the kinetic energy of the flow. And for most of our studies, we will see that our pressure, at least in this course, our pressure would depend on the kinetic energy of the flow. So that's why Professor Chakraborty has taken delta P to vary as half rho u square. Okay, again, he's not saying it's exclusively equal to that, but he says that since the flow is driven by the kinetic energy that is in the flow, then our pressure would vary as the kinetic energy head, that is half rho u square. Okay, then we can write, if we substitute this delta P in this if you substitute the value of delta P in this expression, we'll get the bulk modulus K varies as rho by delta rho into half rho u square. Okay, then just rearrange these terms, you will get that delta rho by rho varies as half rho u square by K. Okay, and the medium of sound, I'm sorry for that. The speed of sound in a medium, that is A, or the sonic speed for a particular medium, is given by K by rho. Okay, so this you can again derive or understand by using some references. Especially it is used in the case of solid mechanics. They use this to quantify the value of the sonic speed in their solid medium, but this is again relevant in the case of fluid mechanics as well. That's why it is relevant here. So the speed of sound in that particular medium, which may be any kind of fluid, that is air or water, for example, in this case. So it is defined as K by rho. So taking this expression into account, you can write delta rho by rho, that it would vary as half rho u square by a square. Okay, then we can write delta rho by rho varies as half rho ma square, where ma is the Mach number. Okay, and you will see that this Mach number in fact plays a crucial role in determining the compressibility effects. For example, if the Mach number is beyond some certain value, we can say that the compressibility effects are much more significant to take into account the density variations. So we cannot solve those kind of flow fields using our conventional incompressible governing equations. So we need to take into account the density variations, and that density variation is considered by understanding the parameter Mach number. Okay, so usually if it is greater than 0.3, then we consider that the compressibility effects are significant, so we cannot consider the change in density to be negligible. Okay, or in other words, if delta rho by rho is less than 5%, then we can consider the fluid flow to be incompressible. Okay, so these are the this is just a way, or I must say, a methodologically. I'm sorry, I'm not getting the correct word. I will say it's just a way to understand how different parameters help us to understand the fluid flow that we have in our hand. So before now, we didn't have any particular parameter to quantify these incompressibility effects. We are saying that change in the volume of the fluid element or change in density, but you can see that there's a separate non-dimensional number that helps us to understand these compressibility effects, which is the Mach number in this case. And this is the way you'll eventually see how there are different non-dimensional numbers that we define in our study of fluid mechanics that helps us to understand the nature of the flow. Okay, so if there's some non-dimensional number fall under certain range, then we can say that this kind of flow will come under this category. Okay, so this is how we deal with such kind of non-dimensional parameters, non-dimensional numbers, and use them accordingly. Okay, so then comes the concept of viscosity. Okay, so viscosity in general, I would say in the simplest terms, is a kind of, can be attributed to resistance that is given by the flow, that is applied by the fluid against any kind of motion that is going through it. Okay, so for example, if there is a relative motion that is being undergone through a fluid, then the fluid will impart some kind of resistance to resist that motion, and that resistance is by the virtue of its viscosity. Okay, and of course there is a formal definition of that, but we will go through it eventually. But this is what I'm trying to say. For example, like if you are trying to uh, walk in air, like just walking in air, compare it to walking in water, you will see there is much more resistance offered by the water than air. So we can intuitively you can say that viscosity of water is higher than viscosity of air. Okay, and here I'm talking about a dynamic viscosity, or mu, that is eventually being defined. Okay, so I'm sorry for this noise. Let us just wait for a few seconds. Okay, I cannot control this because it's going outside of the room, so I cannot control it. Just wait for a few seconds so that this disturbance goes away. Okay, so I think we can continue. I'm sorry for this disturbance. Okay, so then, to understand the concept of viscosity, Professor Chakraborty again used an example of flow over a flat plate. He took an example of flow over a flat plate because it is through it the concept of viscosity, the role of viscosity is most properly understood, or in other words, extensive studies has been done for such kind of flows, for flat plates or the generation of boundary layers, which we'll eventually discuss in the later part of the course, where we can see the considerable role of viscosity in the generation of velocity profile and the pressure profile, okay, or the shear stress distribution. So with viscosity comes to one new concept, that is a concept of no slip boundary condition. Okay, and we'll eventually discuss what a boundary condition is and why this mathematical term has taken its place in a physical study. Okay, we will eventually see why. Okay, but let us consider this no slip boundary condition, because you may relate boundary conditions with something as partial differential equations or ordinary differential equations, but why you are using the mathematical term, you will eventually understand why. So there is the no slip boundary condition, which defines that there is zero relative velocity between the fluid molecule and the walls. Okay, so for example, if this wall is stationary, the velocity of the fluid molecules that are attached to this wall will also have zero velocity. Or in other words, if this plate is again moving with some velocity v, then the fluid molecules will also move with that velocity v. Basically, there will be no relative tangential velocity between the fluid molecules and the wall. So the thing is, no relative tangential velocity. Okay, so the tangential velocity basically mean that the velocity along with the direction of this wall. So we do not know anything about the velocity that is normal to this wall. Again, there are separate boundary conditions to define that. Okay, that boundary condition is defined as a no penetration boundary condition. Okay, that we will eventually see if we encounter such kind of problems. But these are two different boundary conditions. For relative velocity, we have the no slip boundary condition, and for the normal component of velocity, we have the no penetration boundary condition. Okay, so we need to distinguish these two conditions separately. Okay, and again, there Professor Chakraborty discussed about the existence or the origin of this kind of no slip boundary condition, how it occurs. I'm not going to go through that. And again, he also discussed the special case that we already discussed in the last problem solving session, like why there may be certain slip because of the formation of bubbles that allow this flow to slip over the surfaces, rough surfaces. Okay. So now you may ask, like, why there is no slip boundary condition. Okay, so because of the presence, because of the fact that the fluid molecules get stuck in with the surface along which it flows, so there is the effect of this no slip boundary condition is also felt to the fluid molecules that are not stuck with the surface. Okay, so as I mentioned, that if this plate is stationary, then the velocity of fluid molecules along that are sticking with it will also be zero. But you may say, then if it is zero, then the fluid should not flow at all, but that's not the case. Okay, you will see that the fluid molecules just above these molecules that are stuck with the wall has a higher velocity, and again the fluid molecules that are above those molecules has progressively higher velocity until it reaches the free stream velocity. Okay, so you can see there's a certain pattern or profile in this incremental velocity, which is defined as the velocity profile. Okay, so this velocity profile is a consequence of the no-slip boundary condition, and this velocity profile is generated because of the momentum disturbance that is propagated through the fluid molecules by the virtue of the by its viscosity. Okay, so let me try to define it in a simpler, try to define it in a other way, other fashion. So for example, let me just draw some. Okay, so for example, this layer of fluid that is stuck to the plate has zero velocity. Okay, then the layer above it will have a bit higher velocity, because in this case, in the case of floor flat plate, I guess Professor Chakraborty discussed about a generation of boundary layer, which I am not taking in this discussion because it's not that relevant for the problems that we are solving, but it will become quite relevant when we discuss the boundary layer theory. Okay, so so what happens then in the case of floor flat plate, which the example is considered here, the fluid flowing with a certain velocity u or u infinity strikes this flat plate. Okay, and generates a boundary layer. So again, let me use different color. Okay, so I think it would be something like that. Okay, so the fluid molecules that strike this flat plate or closer to the surface of the flat plate have zero velocity. Okay, that's because of the because of the effect of viscosity, that they are having zero velocity. But the fluid layer above that layer that is attached to the wall will experience two kind of forces, two different type of forces. Okay, first is the momentum that is imparted by the lower layer of this particular layer, which will cause it to slow down. Okay, and then again there is another force that is imparted by the layer just above it, which will try to pull it with a higher velocity because of the motion of the fluid far away from the wall. and this interaction between these different layers of fluid is by the momentum disturbances that is being exchanged between these different fluid molecules by the virtue of their viscosity. Okay, and as Professor Chakraborty very beautifully explains, it is because of this momentum disturbance that there is resistance to relative motion between these different layers of fluid. Okay, and this momentum disturbance is because of the viscosity of the fluid. Okay, so I hope this part is clear. And again, Professor Chakraborty extensively discussed like how this boundary layer is generated, how the velocity profile changes at different points in the boundary layer. Again, there's a very thorough discussion in the lecture, but just to save time and knowing the fact that this discussion will not be quite useful at least for this week's assignment, I'm just skipping that part, but it is again very important. So I will suggest that you go through that discussion or that part of the lecture thoroughly, because it's very beautifully discussed by Professor Chakraborty. So I will suggest that you go through that part thoroughly once again, then at least from the concept that we discussed or clarified in this session will help you to more to consolidate your concepts even further. Okay, so lower viscosity fluid will generate a thinner boundary layer, and a higher viscosity fluid will generate a thicker boundary layer. Again I will myself will leave it as an exercise for you students to support this statement, like why I am saying this, how I can say this. Okay, so that is discussed in the lectures. Okay, so I will not take it right away, but it's an important observation that you can make. Okay, so now let us try to define the viscosity that we were so critically discussing right until now. Okay, so consider a particular fluid element that can be anywhere. Okay, so let us consider the fluid element to be stuck at the wall. Okay, for example, just consider this case, and you can also consider the fluid element to be above a certain edge, but again, just to not be confused with this having a zero magnitude here. So I'm just taking it to be at the wall. Okay, consider this fluid element is here, and I'm taking a zoomed in view of that fluid molecule here. Okay, so let us just name these edges of this fluid molecule. That would be A, B, C, and D. Okay, so the fluid molecule, because of the motion of the plate, has moved a certain distance u into delta t, and since the layer above has a higher velocity, so it will move by a distance u plus delta u into delta t, and this increase in delta u is because of the fact that the layer above it has a higher velocity, which is imparted by the free stream velocity. Okay, so and let us name these points as A dash and D dash. Okay, and let us say the angle that this line makes is delta theta with respect to the straight line AD. Okay, then tan of this angle, tan delta theta, would be given by base by perpendicular by base, so it would be this length, that is u into delta t by delta y. Okay, simple trigonometry used here. So we know that for small delta theta, tan delta theta would vary as delta theta. Okay, so and if you need to find the rate of change of this angle, so it will basically be delta theta by delta t. Okay, so dividing it by delta t would give you delta t by delta t as delta u by delta y, and taking limits as delta y tends to 0 in the right hand side and delta t tends to 0 as in the left hand side, just so that we can write it as rate of change of these parameters. We can say that the rate of change of the angle theta, that is the rate of change of the angular deformation of this fluid element, would be equal to du by dy, or in some cases it is in general case it is written as a partial derivative of that of this, because u may not be always be a function of y only, it may be function of x, y, and time as well. But just to make it simpler, I am just saying that we can write it as a complete derivative, that is du by dy, considering that u varies as y only. Okay, so this rate of angular deformation is given by this expression for this particular case. Okay, and now so now we would like to look, given that we have an idea and at least an overview of how the strain rate varies in fluid flows. It's only a particular case that we are discussing. Again, there's a generalized expression for this strain rate. Okay, there is a rate of angular deformation also known as strain rate or rate of shear strain. So there's again a different generalized expression for that, which we will not be covering right now, but as per the discussion by Prof. Chakraborty, I'm keeping it as simple as possible. So the strain rate varies as the derivative of the velocity profile. Okay, so its characteristic length scale would vary as u by L. Okay, that's what I'm just trying to imply. Now we need to find the expression for the shear stress. Okay, like how the shear stresses vary with respect to the applied shear strain, because for example in solid mechanics you might have seen the strain rate versus strain rate versus the stress curve, which gives us the Hooke's law, like up to the elastic limit the shear stress varies linearly with the shear strain. So in those cases it is always the strain, I will just say strain in the case of solid mechanics, but we'll see that in those cases it is a strain rate that is the independent parameter. Okay, so in this case also, our case also, this strain rate or theta dash, as we like to represent it as, is the independent parameter. Okay, and it is the relationship between this strain rate. It is by the, with respect to strain, we will have to find how with respect to this strain rate the shear stress varies in the fluid flow. Okay, because it turns out to be important parameter for our discussion that we discussed in the previous week, like how we would want to find a traction vector or normal forces. So to find the force we need the shear stress. shear stress distribution, right? And to do that, we need to find relationship between the shear stress and the strain rate, okay, or the rate of shear strain in this case. So we need to find relationship between the shear stress and the strain rate. Okay, I hope this part is clear up till now. And this relationship between the shear stress and the shear strain rate or the rate of angular deformation is known as the constitutive relationships. Okay, it's a very important terminology. And the similar, this is named similarly in the case of solid mechanics as well. The rate of the relationship between the stress and the strain is represented as the constitutive relationship. Okay, and in fluid mechanics it is strain rate, because it is discussed in the first lecture itself why we deal with strain rate rather than only strain, because this fluid molecule tends to differ continuously. Okay, tends to deform continuously with the application of a force. So we are more interested in the, not in the total deformation, but the rate of deformation. Okay, so we are dealing with strain rate. So for Newtonian fluid, as the name suggests, a very simple definition for Newtonian fluid would be a fluid that follows the Newton's law of viscosity. Okay, and Newton's law of viscosity is that for this kind of flows, the shear stress varies linearly with the shear strain rate or the angular deformation. It is, for Newtonian fluid, the shear stress will vary linearly with the angular deformation or the shear strain rate. I have to write shear strain rate. Okay. I hope this is clear up to now. Okay, somebody can give a thumbs up or just say yes. I hope it is clear till now, like why we are finding relationship between the shear stress and the strain rate. Okay, I will take it as a yes, hopefully. Okay, so for Newtonian fluid, the shear stress varies linearly as the shear strain rate. Okay, and since it is a proportionality symbol, we need to substitute it with a equality. So we need to take a constant of proportionality, and this constant of proportionality between the shear stress, between the relationship between the shear stress and the shear strain rate is known as a viscosity. Okay, so there is a physical definition or physical understanding behind viscosity, but again there's a very crude mathematical derivation or expression to define viscosity, which is the ratio between the shear stress and the strain rate. Okay, in the case of Newtonian fluids. Okay, again you may ask, like, what about non-Newtonian fluids? Again there is a very robust definition for that, which we'll eventually see. Okay, that in that case we define it as the apparent viscosity. Okay, and the units of these units of viscosity or dynamic viscosity, if I may iterate it as, okay, so it is known as, also popularly known as the dynamic viscosity. So sometimes you may encounter two different kinds of viscosity. It is dynamic viscosity and kinematic viscosity. Again, they have different significance, and in most of the cases we like to quantify this viscosity in terms of kinematic viscosity. Again, for different reasons. Again, as an exercise, I would like you to find out why we like to prefer to discuss these fluid flows in terms of kinematic viscosity. Okay, so that's something that you can look into it. Okay, but in the case of dynamic viscosity, the units of dynamic viscosity are mass into L inverse into T inverse, length scale inverse into time inverse. It will basically be mass, unit of mass is kg divided by length is meter and second. So kg per meter second is the unit. Okay, or in other words, again it is Newton second per meter square or Pascal second. Okay? These are units of the dynamic viscosity. Again, there is another non-dimensional parameter. No, sorry, not non-dimensional. There's another parameter that we can quantify it. This viscosity is by the ratio of this dynamic viscosity by the density of the fluid, which is known as the kinematic viscosity. Okay, and this kinematic viscosity is indeed an indicator of the relative tendency of the fluid to create a disturbance in the momentum compared to its ability to maintain its momentum. Okay, so why you may consider why density is considered to quantify its ability to maintain momentum. So for example, you will see that, for example, if we consider air, okay, we consider air and water as the example that I just gave before. You will see that since water has 1,000 times the 1,000 times density of the uh, 1,000 times density of air, you will see that this momentum transfer from uh, from different layers of fluid, in case of air and water, you see that this momentum transfer from one layer to another is much more rapid in the case of water, because of it creates inertia which resists changes. Okay, that's again a very good way to put it. Okay, so Divyanshu mentions that it's a function of, since density is a function of mass, it creates inertia which resists changes. Okay, that's again a good way to put it. But as I was saying, yeah, so this higher density would result in a higher rate of momentum transfer. Okay, so as Professor Chakraborty might have discussed, that if the density of the fluid was lower, the boundary layer that is generated would be much more greater than the case of fluid in the case of the higher density fluids. Okay, that's again one way to put it. But yeah, I hope it's again definition given, the discussion by, or the reasoning by Divyan is also quite good. The density, since a function of mass, it creates inertia, so it will resist change. Okay, so again that's the good way to put it. Okay, thanks Divyanshu for putting that comment. That's fine. Okay, so now let us look into the origin of viscosity. Okay, so the origin of viscosity, I will just briefly discuss it. That is the for liquids, it is the intermolecular forces of attraction between the fluid molecules that generates the viscosity. But in the case of gases, it is the transfer of molecular momentum. So as the temperature increases in the case of liquids, these molecules will try to move away from each other, and that's why since molecules move away from each other, the intermolecular forces between these molecules will reduce. That's why as the temperature increases, the viscosity, the dynamic viscosity of fluid will go down. Okay, similarly in the in contrast, in the case of gases, since this I'm sorry, this viscosity is Bhaskar. Okay, so Bhaskar, if you have joined right now, so my mic is not my speaker is not working. I think I'm not able to hear you. If you have any doubt, but you can just write your question in the chat box. Okay, I will just try continue the lecture, but once you write your question, I will see it and answer it. Okay, I hope that's fine. Okay. You can just write in the chat box. Okay, so in the case of gases, this viscosity is perceived as a transfer of momentum between the fluid molecules, okay, or molecular momentum. So as if there's more collisions between the fluid molecules, okay, of course gases can be considered as fluids, so between these gases molecules, then the viscosity of these gases increases. So as temperature increases, the vibrations between these of the molecules will increase, and thus the viscosity will also increase. Okay, again there was a very thorough discussion between the kinetic theory of gases by Professor Chakraborty, so I'm not going to that part, and it is through that we come into the picture of how to define Mach number in this kind of flow regimes. But just for saving time, I'm not going to go through them right now. But if you have any doubt, you can just put in the discussion forum, or because for this week's discussion, question answer part, I don't think that will be quite relevant, but again it's important to know. Okay, so the final conclusion that with that discussion by Professor Chakraborty was that for an ideal case, the Knudsen number that we initially defined as the mean free path, the length scale of mean free path over the characteristic length scale of the flow, is the Knudsen number. So we found out that for ideal gases, this Knudsen number varies as the ratio of Mach number over the Reynolds number, or Mach number varies as the ratio of the Knudsen number times the Reynolds number. Okay. So Bhaskar, you had some doubt, you can just put in the chat box. Okay, the speaker is not working, so I will not be able to hear if you speak. Okay, sorry for that. Okay, so yeah, so as I mentioned, for Newtonian fluids, we saw that the shear stress varies as the strain rate. Okay, it varies linearly as the shear strain rate. Now for non-Newtonian fluids, Professor Chakraborty mentioned that this shear stress can be a function of some power of the shear strain rate, let us represent as theta dot to the power n, where we can say that this theta dot n follows some power law, and the shear stress varies as some power of theta dot n. Okay, so we can write tau is directly proportional to theta dot n to the power n. Okay, not dot n, theta dot to the power n. Then we can write tau as k times theta dot to the power n. Okay, then we can write, just to find a similar expression as tau is equal to k theta dot, or is equal to mu theta dot. So we can write it as tau equal to k theta dot to the power n minus 1 into theta dot, and this product theta dot n minus 1 into theta dot will give you again theta dot n to the power n, and we are just dissociating it. So we can write tau as k theta dot to the power n minus 1 into theta dot. So we can write it as tau is equal to mu a into theta dot, where mu a is the apparent viscosity. Okay, so I think the discussion is clear up till now, because this expression, related to this expression, I have some questions in for today's discussion. So I hope you're clear, or in other words, you can just write mu a is equal to k into theta dot to the power n minus 1. Okay, so again, then there were some examples discussed by Professor Chakraborty of different kinds of fluids, and how the relationship between the shear stress and the shear strain rate varies from different types of fluids. In the case of ideal fluid, since there is no viscosity would be 0, then we will have no shear stress generated in the case of ideal fluids. Okay, so no matter how much we vary the shear strain rate, no stress is generated because of the fact that the velocity gradients is velocity gradient in the flow field would be very small. Okay, or it will be apparently absent. Then in the case of Newtonian fluids, as we mentioned, this shear stress very linearly with the shear strain rate, so we will have a linear curve. Okay, then for dilatant fluids or shear thickening fluids, we will have that the curve will vary in this fashion, that the shear stress will increase with time. It will not give a linear curve, but it will increase with time as it will increase as the theta is increased. Okay, so it will not be a linear relationship. And similarly, there is pseudoplastic fluids, for example polymer suspensions, which will give this kind of relationships. And finally, there is Bingham plastic, where again it follows a linear relationship, but there has to be some threshold value of shear stress that has to be generated up till which the fluid will not start to flow. Okay, so for example, there is toothpaste, like up till until we apply some certain kind of force, it will not start to flow. That way toothpaste can be characterized as a Bingham plastic fluid. Okay, then again there is thixotropic and rheopectic fluids, that is where the apparent viscosity in this case is a function of time, where with time the viscosity goes down. Those kind of fluids are known as thixotropic fluid, and time, if the apparent viscosity increases with time, these kinds of fluids are known as rheopectic fluid. Okay, So there was one example taken by Professor Chakraborty. I will just quickly go through it once. I think, and this example, like I myself have gone through thoroughly in the lecture video, and I think it is very beautifully taught, discussed for quite a few time. But uh, just so that you are able to correlate the concept that we discussed up till now, I will just go through it once. If you have any doubt, you can ask. Otherwise, we will just go through this problem once, and then we will go to this week's discussion. Okay, question and answer part. Okay, so this example was taken by Professor Chakraborty. There are two masses attached to a pulley, which are attached by a string, and it is this mass m1 is sliding over the surface, and there is a thin liquid layer between this mass m1 and the surface, which I can say which encourages the motion of this or act as a lubricant between this mass and the surface, which encourages its motion. Okay, but by the virtue of its viscosity, again it will tend to oppose the motion of mass m1, but it's act as a lubricant in the fact that the frictional forces because of the viscosity would be much more lesser than the friction force that would have been generated if the mass was just moving over this surface. Okay, that's why it's just an example of lubricant, and that's why we're using a narrow gap limit. Okay, narrow gap height h. And the approximation that were taken to simplify this problem was this pulley is a massless pulley, or massless and frictionless pulley, and this is an inextensible string. Again, Professor Chakraborty again very beautifully describes how this approximation simplifies the problem. Okay, then we draw the free body diagram of these different parts of this diagram. For the pulley, we draw the free body diagram where the where the mass, if at all it was considered, would vary in this manner, and the two tensions because of the string are shown here. Then if we consider the if we find the summation of all the moments with respect to the center C, we will find that T1 minus T2R would be equal to half into mp r square into alpha. Now, since half mp r square is the moment of inertia with respect to this central axis C, and since the mass of the pulley is 0, so T1 minus T2 into R would be equal to 0, which since R is not equal to 0, it would basically imply that T1 is equal to T2. That's the first conclusion that we get if we consider a massless pulley. Okay, for the mass m2, this mass m2 again is a simplified case, so we are considering that first. The free body diagram shows that the mass will act in the downward direction, and the tension T2 will try to pull the mass in the upward direction. And for example, if the string is cut, this mass will tend to flow in the downward direction. So T2 minus m2g would be equal to m2a. Okay, simple equation of motion for this mass. The third mass is the most interesting case, because here we are seeing the interaction of fluid between the we are seeing the interaction between the fluid and the solid surfaces. I'm sorry. Okay. I'm sorry for this coughing. Okay, so here now we see again the mass of the this block will act in the downward direction, and there will be corresponding normal reaction. The tension of the string will try to pull this mass in the right hand side, but the frictional forces because of the fluid will resist its motion and will thus act in the opposite direction. Okay, so this is the free body diagram of this mass m1. So these frictional forces will vary as tau times a, which is area of this block, and tau is the shear stress because of the fluid. Okay, shear stress is generated because of the fluid, or basically the motion of shear stress because of the motion of this block over that particular lubricant, okay, or the fluid film. Okay, now we can assume that if the gap between the mass block of the mass m1 and the surface is very very less, that's how we consider these lubrication problems. We consider a very thin gap limit. Then we assume that the velocity would vary linearly from the bottom of the surface to the block. Here, of course, this is generated by from considering the no slip boundary condition. Since the lower surface is at 0 velocity, so the fluid molecules at the lower surface is 0, and since mass m1 is moving with velocity v, I'm again sorry, moving with velocity v, then the fluid molecules attached to this mass m1 will have a relative velocity of v with respect to the molecules that are attached to the lower surface. Okay. So since this fluid film has a very thin, very small height, then we can consider this velocity to vary linearly. Okay, it's a very good approximation that is that has been discussed in various literature. So this is a very good approximation that we can take. Like if the gap ratio is very less, if the gap between these two surfaces is very less, then we can consider the velocity to vary as linearly. Okay. Then we can write the frictional forces Fr is equal to tau into A, where tau is the shear stress. Or we can, considering a Newtonian fluid, then we can write it as mu into theta dot into A. And since we told that it varies linearly, so for example, then we can write du by dy would be equal to v by h. Okay. For example, then you can consider the velocity profile would be something like v into y by h. Okay, thus it's a linear relationship, okay, between u and the this coordinate axis y. Okay, now for the equation of motion for mass m1 can be given by normal direction is equal to m1 into g. Basically these forces balance each other. The tangential forces along the x direction would be summation of fx is equal to m1 into a1, where the a is the acceleration of this this block. Then we can write t1 minus fr equal to m1 into dv1 by dt, or fr is, as we found out, fr is mu, I can just write it, it is mu va by h. Okay, so t1 is, fr is mu va by h, then t1 minus mu v by va by h would be equal to m1 into dv1 by dt. Okay, let us consider this equation number 1. Okay. So for mass m2 we know that m2 g minus t2 is equal to m2 into dv2 by dt. Okay, we found out from this free body diagram. Okay. So now T1 is equal to T2, that we found out from the free body diagram from the pulley. Okay, since the mass of pulley was 0, so tension this in those two strings was equal. Okay, so we found out that T1 is equal to T2. So we need to substitute T2 by T1, and we consider that since the string is inextensible, so V1, there is a velocity of the block 1 and the velocity of block 2 would be equal, and let us consider the velocity to be equal to V. Okay, then we can write T1 as minus m2 dv by dt plus m2g. Okay, thus just modifying this expression considering these two approximations. Then substituting the value of this T1 in equation number 1, we can write, like substituting the value of this T1 in equation number 1, that is this equation, then we can write T1 okay, so is the screen frozen or something? Like, are you able to see something? Like, it seems the screen is frozen. So is the screen frozen, like, or it is all right? Can someone please say yes or no? You can just write in a chat. Okay, I'll try to reconnect. It is okay. Okay then. Okay, if it is not causing any issue, then okay, then it's okay. Okay then. If it's okay, then I will like to continue. Then we can substitute it in equation number. Where was I? Substituting in equation number 1, then we can write minus m2 dv by dt plus m2g minus mu va by h is equal to m1 dv by dt. Okay. Then again rearrange this expression to write as m1 plus m2 dv by dt is equal to m2g minus mu va by h. Okay. Then just using the concept of separation of variables, we can write dv by m2g minus mu va by h is equal to 1 by m1 plus m2 into dt. Okay. Now if we integrate it from 0 to v, we can write it as integration of dv by m2g minus mu va by h from 0 to v. m1 and m2 are constants. We can take it out of the integration. We can write integration dt from 0 to t. Okay. Now you may ask, like, why you are not considering taking out of an integral? Because v may not necessarily be a constant, so it can vary with time. So we need to consider that variation. Okay. So there was a very interesting case that was described by Prof. Chakraborty. What about the steady state case? Okay. So I'm saying that velocity can vary with time, but for example, if the flow reaches this problem reaches a steady state, like the two forces, the friction by the viscous forces, frictional forces because of the viscosity, and the motion of this string balance each other at some point, then the velocity will reach a constant value. Okay, in that case, from this expression, dv by dt would be equal to 0. Then m2g would be equal to mu va by h. Okay. For steady state, let me just write it. For steady state, dv by dt would be equal to 0. That would imply m2g is equal to mu va by h, or the steady state velocity v would be equal to m2 g into h by mu a. Okay. So can you please wait 1 second? I'm thinking, I'm seeing that my screen is freezing, like while I'm recording it. So okay, it's freezing, so I will just try to reconnect. Okay, just stay here for a while. Yeah, Bhaskar, you have raised hand. So yeah, can you I'll just see in the chat box have written the question. Okay, so Bhaskar, you have still raised your hand. So kindly, can you please write your question or any doubt that you have in the chat box while I'm trying to reconnect the screen. Okay, others please wait. Okay, I'll just try to reconnect the screen. It is lagging from my end a lot, so I'll try to reconnect, then see whether the problems is sorted out or not. Okay, so Bhaskar, meanwhile, please write your question in the chat box so that we can I can just look into it and discuss in among everyone. Okay. So everyone, is the screen visible? Simple yes or no, be okay. Okay, screen is visible. Oh, so I think there's a lot of lag between this my screen and my iPad, so that's why I'm facing some issue. Okay, sorry for that. So the steady state value of the velocity, like when these frictional forces and the force because of the weight of this m2 mass m2 balance each other, then the steady state velocity would be given by v is equal to m2g h by mu a. Okay, and if you have any doubt, you can ask regarding this problem, because I think there should not be, because Professor Chakraborty like very beautifully discusses this example, and in fact, without doing any calculation, he tells the variation of the relationship between v and t. So I think that's extremely impressive from his end. But again, so if you have any doubt, you can just go back to his lectures, revisit them, and then we can discuss in the next week. Okay, so discussion part for this week is up to here. So now let us look into some questions. Okay, that will be similar to the ones that has been asked in this week's discussion. So let us try to look into one of them. Okay, look into them one by one. Okay, so is the question answer part visible? Are you able to see that PDF? Yes. Okay. Thanks, Divyanshu. Thanks. Sorry. Senavas. Thank you. Okay. So, okay. So there seems a lot of lag from my end. Okay. Technical issue. Okay. Now it's fine. So the first question is, then this is again statement type question. You need to just say whether the statements are correct or not, and whether statement two supports the statement one. Okay. So the first statement is, Reynolds number is valid only for accelerating fluids for which we can calculate the inertial force component. The second question is, Reynolds number is in general defined as a ratio of inertia force to viscous force. So can you say which of the options are correct? I would say it's a bit not, it does not seem that difficult, but it can be technically difficult because, say, if you are new to this field of fluid mechanics, so in that case it's very hard to visualize these statements in the best way possible. So something might seem quite apparent, but that's not always correct. So it's an interesting question, that's why it is discussed here. But you can at least put your options, like which you think is correct. Okay. Just go to the statements. Like if you have any, like, option D, both statement 1 and 2 are incorrect. Okay. Saurabh says option D, and others. Divyanshu says D. Statement 2 correct. So are you, Shenawaz, are you implying that option C is correct? Okay. So the correct answer is option C, that statement 1 is incorrect but statement 2 is correct. Why? Because intuitively, I think, I don't know, I'm not sure, but we might have discussed that Reynolds number is actually the ratio of the inertia force over viscous force. Okay. So, yeah. So the question directly inherently comes into the picture that if there is no accelerating fluid component that would generate this inertia, should there be, should the Reynolds number be defined in that case? Okay, so but then, so the answer is okay, yeah. So the answer is yes, because even though the fluid is not accelerating, okay, even if the fluid is not accelerating, uh, I'll just give one example. That's why I told, like, it's difficult to understand intuitively. I'll give you an example. Okay, so for example, you are dealing with flows that do not have a particular direction of flow. Like, for example, in the case of pipe flows, like, I'll give an example. In the case of pipe flows, uh, you see that the velocity has a particular direction. So example, from left to right. Okay, from left to right, it has a particular direction, and given the, if you change the pressure conditions, there might be some initial acceleration. Okay, so there might be a scenario where you can achieve some initial acceleration of the flow, and after some time it will reach a steady state. Okay, so in that case, of course, there are some possibilities of inertia, and then the definition of this existence of inertia force, it is m into dv1 by dt, becomes quite relevant. But there are some flows, for example, uh, for example, if you consider a flow in a cubicle box, or for example, if you consider the flow in your room where you're staying right now. So in that case, in the room, you may not have, and in the room, say example, you're staying in a room and might have switched on your fan, okay, switched on your fan, that is generating some swirling motions of the flow in the room, okay. And these motions, these circular motions of the fluid molecules, also known as eddies, do not have a definite direction or direction of motion, okay. They have certain motion, that is what is the angular velocity of these eddies, that by which they rotate. They have some certain velocity, but these do not have any particular direction of motion, or they don't have a particular direction of rotation, in fact. So they are random. Their motion is random in the room, okay. But then also in these kind of examples as well, the Reynolds numbers can be defined, where the Reynolds number for this kind of flows is actually defined as RES U RMS times LC, nu times LC, okay. So I am sorry if it may not be, you may not understand it right away, but I'm just saying the cases where these kind of situations can be there, okay. Where URMS, or RMS, is the root mean square velocity, or just to simplify it, this UC you can replace by URMS, you can replace by UC, okay, or the characteristic velocity. So the characteristic velocity in this kind of scenarios, or in this example, is the RMS velocity in this particular room, the RMS velocity of this motion of eddies. For example, if you consider a particular point, then you find the RMS velocity at a particular point, and then you define the characteristic velocity of this kind of flow, okay. So this is again a way to define the Reynolds number, which again will give you an overview of a overall idea of the variation of the inertial force by the viscous force, okay. I'm again sorry, I think it seems I was correct previously. It would be in fact LC by nu. Viscous force has to be in the denominator, right? That's what quantifies the Reynolds number, yeah. So so this again gives us the Reynolds number of this particular kind of flow. So here you can see there is no apparent acceleration of the flow field, but there is motion, and this motion is characterized by the RMS velocity, okay. So in this kind of flows as well, we have, or we define Reynolds number, but we cannot say that if the flow is not accelerating, we cannot define the Reynolds number, because there is no inertia force, okay. So you will see eventually when we discuss the non-dimensionalization of the governing equations, you will see how it's actually the characteristic velocity that we use to define the Reynolds number, rather than the inertia of the flow field, okay, or the component that causes the inertia force, okay. We'll see it's actually the characteristic velocity of that particular flow, okay. So I know it can be difficult, it may be difficult to understand right away, but again, these are the scenarios where you need to have a factual understanding. You need to know the special cases that may arise, which may result in the general statements that is written here. It's a very general statement, that these general statements may become incorrect, okay. So I hope it is clear. I'm sorry if it's not clear, but it's difficult to understand right away, but I'm just mentioning these special cases where this might be correct, okay. So this is this definition remains valid, okay. So I hope it's clear. Ketan, is that fine if you're still in the meeting? Okay, Ketan is still there. I hope it's fine. Okay, thanks Ketan. Again, it's a good thing that you pointed out, but yeah, it's difficult to understand at the first go itself, okay. Okay, I hope everyone also understood. If you have any doubt, let us just discuss after this Q&A part, because there will be doubts, and I accept it myself, okay. But there can be special cases as I mentioned here, okay. So let's look at question number 2. Which of the following statements are incorrect? Okay, which of the following statements are incorrect? The no slip boundary condition refers to zero velocity between fluid and the solid at their points of contact. The no slip boundary condition is applicable only for Newtonian fluids. The origin of no slip boundary condition can be understood from the concept of momentum exchange between fluid molecules, or D, none of these. So which of the statements are incorrect? Okay. So I will request that you go through the statements very properly. There are some keywords that you need to understand. Then only you say your answer. Okay. At the first go, you may feel like it is what I was discussing throughout the session, but again I was mentioning those keywords. Like, yeah, in this case only I can define the no slip boundary condition. It is this direction of motion of velocity that I can define no slip boundary condition. The other direction I have no idea. So Divyanshu says option B is incorrect. Okay. So others, can you please put in your comments or ideas, or you adhere with the answer of Divyanshu? Okay. Ketan says it's B. Shubham says it's B. Shenavas says it's B. Okay. So let us go discuss this question. So the correct answer or answers in this case would be both A and B. Okay. So first let us discuss B, because most of you answered it correctly. Why B? Because this no slip boundary condition is a universal condition that is applicable for both Newtonian and non-Newtonian fluids, and it is by this condition that we are able to solve the much celebrated Navier-Stokes equation that you will eventually see what it is. This is basically the governing equation of fluid flows. Okay, so it's applicable for both Newtonian and non-Newtonian fluids. Okay, because the definition of Newtonian and non-Newtonian is just the type of fluids that we choose, or basically the constitutive relationship between the stress and the strain. But this condition is applicable for all kind of fluid flows. Okay, of course there are some special conditions, but say if you are reaching the high Mach number flows where there can be slip across the boundaries, but we are not discussing that regime. But for most of the cases this is universal, and it's valid for both Newtonian and non-Newtonian fluids. Now comes the second statement. It is refers to zero velocity. So I mentioned that it is actually the tangential velocity component, the velocity along the direction of the motion of the plate. Okay, and not the normal velocity component. So the slip velocity no slip velocity condition is referring to the tangential velocity, because that's where we can perceive slipping, right? If I say the flow is slipping with respect to this wall, it will basically mean that this wall and the fluid molecule has different velocities along their direction of respective direction of motion. Okay, so if Vf is not equal to Vp, then only I can say that there is slipping. So I do not know what's happening to Vn or Vfn. So I do not know about that. So that's how we define the no slip boundary condition. There is a relative tangential velocity change in the tangential velocity of the fluid and the solid at their point of contacts. Okay, so is it clear? It's very technical aspect. It's easy to miss out, but I hope it's clear. Okay, thanks Divyanshu. Okay, so let's look into the next question. Again, it's a simple graph that we discussed just few moments before. Which of the colored lines in this figure does not represent a fluid flow with constant coefficient of viscosity? So option A is blue and black. Blue and black. Option B is blue and red. Option C is red and blue. Option D is black and green. So which of the colored lines in the figure does not represent a fluid flow with constant coefficient of viscosity? So can you try? We just discussed this option D, black and green. Okay, nice. Others, can you put in your comments? is blue and red. uh, just to rectify the question is does not represent a constant coefficient of viscosity. Think of it as a equation of line. So how would the line look? Just say y equal to mx relationship plus c. In fact, again, this makes in fact more sense. So when do I say that the slope of a line is a constant? Like, so slope of a line is a constant value. Okay. So okay, think in that way. So the correct in that, if you think in that line, the correct option is D, that is black and green. Okay. So here you can see that these lines, black and green, does not vary linearly with strain. Okay, the stress in this case does not vary linearly with strain. Then you may again ask, then what about option this blue line? Like, it also has some variation, right? It's not varying linearly from starting from the origin. But if you consider that, if I consider this shear as something like T as T threshold plus some constant mu into theta dot, then this equation again remains valid and the viscosity is constant. Okay, it is just the fact that there has to be a certain threshold stress that we need to generate to start the motion of this fluid. That will again once the fluid is in motion, then we can correlate it with the strain rate. But in that case as well, the constant or the viscosity would remain constant. But in the case of this dilatant fluid, and this was, if I again forgot its name, dilatant and pseudoplastic, if I'm not wrong. Just I will check it once again. Dilatant and pseudoplastic, right? The other one is, yeah, pseudoplastic. Yeah, dilatant and pseudoplastic kind of fluids. You can see that these do not have a constant slope, but it varies with the strain rate. In fact, it's a function of the strain rate. Okay, so there's not a linear relationship. Okay, that's why this does not represent a constant coefficient of viscosity. Okay, the viscosity in fact would become a function of the strain rate. Okay, in this case it will be mu would be function of the strain rate. Okay, a toothpaste, yeah, there was a very good example, toothpaste, right? Like when you open the cap of a toothpaste and just like even if you put it upside down to generate the motion because of the effect of gravity, you will see that the toothpaste won't come out that easily. It will remain stationary. But once you apply some stress on the toothpaste bottle or pack, the toothpaste will start to flow. Okay, and that application of that stress that you or force that you do to squeeze this toothpaste out is in fact this threshold stress that you generate. Okay, and once you do that, the toothpaste starts to flow. Okay, and again, I just took a very generic example. Okay, something that Professor Chakraborty also took himself. You can just Google it yourself as well. Look into some examples of pseudoplastic fluids. Oh, sorry, Bingham plastic fluids. I think you asked Bingham plastic, right? Yeah, Bingham plastic fluids, and then you'll get some more examples that will make it more interesting for you to understand. Okay, so it's fine, sort of. I had one example in mind, the most generic example discovered by Professor Chakraborty. I also reiterated the same thing. But mathematically, this is what it means. But that, okay, sorry, yeah, and I don't know. It will be some sort value that is not equal to 1. Okay, I do not know. We have to experimentally look into it. Like, what's the value of this kind of fluids? Okay, I do not know myself. So it has to be some positive value, right? Say if we consider it, say to be a parabolic curve or quadratic curve, then n should be greater than 1, right? Then it will show this kind of behavior. No. For dilatant is this one, so it will be greater than 1. Okay, it should be greater than 1. Then let us look into next question. It is question number 3, so it is 3. Then let us look at question number 4. Again it is statement type question. So these first 2 lectures, or in fact 3 lectures, I guess, would be very conceptually heavy, but it's again very important to set the base for the rest of the course. So that's why these kind of statements are coming into picture. Kinematic viscosity is the ratio of the relative tendency of the fluid to propagate momentum disturbance to its ability to maintain its momentum. Okay. It is defined as the ratio of fluid density to the dynamic viscosity of fluid. So which of the options are correct? Okay. Just read the statement, look into your notes or something that I already discussed myself. Divyan should give a very good example or good understanding why. Okay, Saurabh says A. Others, can you just, what's the definition of nu? Shanawaz say D. Okay, so if you look into it, the kinematic viscosity is defined as the dynamic viscosity or just viscosity in general, because in most cases this dynamic viscosity is in fact defined as viscosity, but here they have properly mentioned as dynamic viscosity. But sometimes if they're only saying viscosity, then it will basically mean the dynamic viscosity, because as per the literature, if they're saying viscosity in the textbooks, it means the dynamic viscosity. But to define kinematic viscosity, they will explicitly mention that they're discussing about the kinematic viscosity. So kinematic viscosity is in fact the ratio of this dynamic viscosity over the density of the fluid. Okay, so in that case, this option statement 2 becomes incorrect. Okay, then it means that this can be correct, right? And this is not possible because statement 2 itself is incorrect. So the option A, C and B can be correct. So option B is eliminated. Now look into the definition of kinematic viscosity. So we told that it is the relative density of the fluid to propagate the momentum disturbance. So mu, as we look into it, was the relative tendency of the fluid to propagate the momentum disturbance. So as the dynamic viscosity, if it's higher, then the fluid will have a higher tendency to propagate. Yeah, Shenavas is correct now. So option C is correct. Okay, so as mu is more, then the fluid will have a higher tendency to propagate these disturbances. So these disturbances will go up to higher distances. Okay, and if density is higher, as mentioned by Divyanshu, it represents the inertia. Yeah, then it will have a tendency to resist the change in its momentum. Okay, so statement 1 is correct. So it will mean that the correct option is option number C. Okay, this is the correct option. Okay, so let us look into question number 5. It's a bit mathematical, so I would like you to have your calculators or your notebooks in front of you to solve this problem. Okay, so the question is, for a non-Newtonian fluid obeying the power law rheology is the study of this viscosity, to determine the viscosity of the fluids, the shear stress and the rate of angular deformation, or shear strain rate, can be rated as tau proportional to theta dot to the power n. Okay, if for this liquid the power law index n is 0.8, then by what percentage will the apparent viscosity change on increasing the shear strain by 5 times? Shear strain rate by 5 times. Okay, so it's a long question. I will request you to go through it once again. It's on the screen. Try to solve it using your pen and paper, and of course a calculator, because now you're using with exponents, so you need a calculator to evaluate it, or in mobile phone so you can do. And then tell me how this apparent viscosity changes. Apparent viscosity, why? Because now we are dealing with non-Newtonian fluids, so dynamic viscosity does not have its relevance right now, but this is apparent viscosity that becomes the quantity of importance. Okay, so let me give you some hints. Those who know just can try, but those who are finding it difficult or not difficult, like if you just join the session right now and you do not know the formulas, so for non-Newtonian fluids, the shear stress had a relationship of uh, tau theta k theta dot n minus 1 to the power theta dot, where k into theta dot to the power n minus 1 was the apparent viscosity mu a. Okay, so keeping that this equation in your mind, can you try to solve this question? You need to find the change in the apparent viscosity if you want to increase the shear strain rate by 5 times. Okay, and value of n is also given, n is 0.8. Okay, so with these equations in your hand, I think it is quite simple. You can give it a try. Okay, so I'll give you, say, what's the time? I'll give you till 7:40. In fact, 7:41. Try it out and then tell me the answer. Okay. Write the option. So, are you able to do it? Treat it as two separate cases. Okay. Okay. Again, a key, I can say. I will say one hint would be that k would remain constant in both the cases. Okay. You can treat it as tau 1 as k, sorry, k theta 1 to the power n minus 1 theta 1, equal tau 2 k theta dot 2 n minus 1 by theta 2. Or you have that mu a1 is k theta dot 1 n minus 1 and mu a2 is k theta 2 dot n minus 1. Okay, this is the apparent viscosity. Then you are told that mu a2 is if you consider like the final value of the viscosity, apparent viscosity is uh, sorry, then you need to find out, right? You need to find mu a2 by mu a1. Okay, then you can write something as k by theta 2 dot n minus 1 as k theta dot 1 n minus 1. Okay, then this, since the k is constant, it will cancel out. Then you're left with mu a2 by mu a1 is equal to theta dot 2 to the power n minus 1 and theta dot 1 to the power n minus 1. Okay. It's a very simple relationship. You are told how theta 2 and theta 1 are related, and n is also given. Now can you tell me what's the value of mu, or what's the relationship between mu a2 and mu a1? I'll give you one more minute, I think. Then I'll show the answer, and then we can look into the next question. Sir, will it be theta to the power n? No, no. Apparent viscosity is defined as this, right? So mu a1 would be k theta dot to the power n minus 1, and mu a2 would be theta dot to the power n minus 1. So it would be n minus 1, and its n is also given, 0.8. So can you tell what would happen? Okay, yes. Okay, so I think, or I believe that all of you are approaching in the right direction, but just to save time, for the sake of saving time, let me just try to show you the solution, because it's whatever written is the way they need to do, but I have not put the numerical values, so we do not know how it will be, right? So let us look into the solution once, just for once, and then we can see. I know definitely that you are going in the right direction, but just for saving time, I'm trying to show the solution. Okay, so we have that shear varies as theta dot to the power n is 0.8. Then we know that the apparent viscosity is given by mu a is equal to k into theta dot to the power n minus 1. Then mu a1 would be k into theta dot 1 to the power n minus 1, and mu a2 would be theta dot to the power n minus 1. Theta dot 2. Then theta dot 2 is 5 times theta dot 1 as given in the question. Okay, what happens to the apparent viscosity when we increase the shear strain rate by 5 times? Okay, then mu a2 by mu a1 would be theta dot to the power n minus 1 divided by theta dot 1 to the power n minus 1. Okay, since the both have the same powers, we can take it as common. It would be theta dot 2 to the theta dot 2 or theta dot 1 to the power n minus 1. Then mu a2 by mu a1 would be 5 to the power 0.8 minus 1, because theta dot 2 by theta dot 1 is 5. Then we have that mu a1 by mu a2 by mu a1 is 0.7248, or mu a2 is 0.7247 72.78 of mu a1, or mu a2 is 72.47% of mu a1. Okay, so it will basically mean that if you want to do, say, mu a1 minus mu a2, because you need to find a difference, an increase or decrease, then it will be mu a1 minus this value, right? This value, sorry, substitute this value for mu a2, we will get minus 0.7248 by mu a1, then it will be something equal to 0.27522, okay, of mu a1. Or it will basically mean that it has increased, or it has decreased by 27.52%. Okay, so mu a2 has increased by 27.52%. Okay, because see, clearly see here, mu a2 is 0.7247 of mu a1. It will basically mean that it has decreased, but how much? By how much? It is decreased by 0.27522 or 27.52%. So the correct option would be option number B. Okay, is it is the question complete, like, or pseudo-plastic? Yeah, yes, it can be, since you're seeing that the power of n is less than 1. Okay, let me just check. Yeah, it should be something like that. Yeah, you can say that. Okay. Oh, sorry for that. So is it clear till now, the calculations part? Was it clear? Okay, so all of you, like, is the calculations part clear? Okay, then let us proceed to the next question. It's question number 6. Again, a statement type question. The viscosity of an ideal gas increases with the increase in temperature. In the gases, the notion of viscosity arises as a result of transfer of molecular momentum between different layers of gas molecules executing random motions by the virtue of their thermal energy. So which of the options are correct? A. Okay, so others? Okay, so again, the correct option is A again. So we already saw that the perception of viscosity in the case of gases is by the virtue of the momentum transfer because of collision between these gas molecules. So as the temperatures increase, the frequency of the collision between these gas molecules will increase, because the gas molecules will again start to vibrate even more when the temperature increased. And again, there's a detailed derivation done by Professor Chakraborty in the lectures. I would just suggest that you go through them once, so that this conceptual statement that I'm giving has a mathematical proof for this. Okay, so you will see that kinetic energy of these gases become a function of temperature. No, that's why, yeah, they're mentioning that if we increase the temperature, right, what happens to the viscosity, right? Because the ideal gas by its definition has to be now, even if the molecules are far apart, now if we increase the temperature, like chances of collision between these gas molecules will increase, right? Because the kinetic energy increases, and that's why viscosity, even if it is zero initially, they will increase with time as the temperature is increased. Okay, and the same thing is the discussion that I have done now is discussed in statement number 2. So option A is correct, where statement 1 and 2 are correct, and statement 2 is the correct explanation of statement 1. Okay. So let us go to the next question. Oh, this diagram. Okay, this is again very interesting diagram that we discussed in the start of this class, and it was discussed very nicely by Professor Chakraborty. So let us go through it. Density may be mathematically represented as rho is equal to delta m by delta v, where delta v tends to some value x. Okay, where delta m is elemental mass and delta v is elemental volume. Ls is the length scale of the elemental control volume. Which of the following is correct? Should x be equal to 0? X is sufficiently large volume compared to the macro scale objects. Density does not depend upon should depend upon the extent of the elemental volume, or none of this. So which of the options are correct? Can you tell? We discussed it in the start of the class. In fact, we used this diagram. We told that this delta V should have a certain value. If I'm not wrong, Divyanshu, I guess he asked, what does the characteristic length scale mean? Or what's the length scale that we're implying mean in that case? And what does L cube this mean? So, yeah. Any guesses? Can please guess a bit faster because we have 2 more questions to discuss and we are running out of time. So just give a wild guess. It's completely fine. We can only learn by option C. Density does not depend on the extent of elemental volume. Okay. Others, can you please give your comments? Okay, it's completely fine. Again, it's for the sake of saving time only I am having to rush it a bit. Otherwise, I would give it ample amount of time for discussions. But just for saving time, at least for today. So the correct option would be none of this. Why? Because see, we saw that if I go back to the discussions, let me just go back to save everyone's time. That will be, hope the screen is visible. Yeah. So here, while defining density, we told that this delta V ideally should approximate to delta V star, where V star is a volume that we have characterized using the mean free path of this elemental or of this fluid molecule. Okay. So this mean free path of the fluid molecule is much more lesser than the macro scale, where macro scale of the fluid flow is defined by the characteristic length scale of the fluid motion. Again, there have been extensive discussion about what is the characteristic length scale of fluid motion and how it is different from the mean free path of the fluid molecule. Okay, so keeping that idea in mind, since this x, they are saying that it should sufficiently large volume compared to macro scale regions, is again wrong. Okay, it should be in the lower length scale, approaching the, I will intend not say lower length scale, but actually should remain close to the mean free path of the fluid molecule. So this option is incorrect, this option is incorrect, and it indeed depends on the elemental volume, because this diagram itself shows like how a choice of length scale within this range gives a correct value of density. So that's why this is also incorrect. So the correct option is D, none of this. Okay, it should depend on the on the mean free path of the fluid molecule. Delta V should have a volume that is related to the mean free path length scale of the fluid molecule. Okay. Next question is, if the system length scale of the elemental control volume is less than the mean free path of the molecules, which of the zones will be associated with the density estimation? Okay, so let me zoom out a bit. Yeah. Question number 8. If I'm not wrong, it is question number 8, right? Yeah. So which of the zones does it signify? If L is less than lambda, it is a mean free path, which zone does that length scale represent in this graph, figure 2? Again, quite simple. I just discussed right now. In fact, it's just option B. Zone 2. Let's read the question again. If a system length scale of the elemental control volume is less than the mean free path of the molecules, then which zones will it be associated with the density estimation? We saw, right, if the value of the characteristic length scale is lesser than the mean free path, then it tends to, yeah, it's correct, it tends to show some fluctuations in the measurements, because the continuous hypothesis becomes invalid in that regime. So there will be fluctuation in density measurement. So the correct option is option number A, okay, or zone 1. Okay. So the final question is, state true or false the choice of length scale pertaining to zone 3. Okay, zone 3 is this one. LS corresponds to macro scale objects, accurately gives the local variation in density. Is it true or false? Again, something that we just discussed. Any comments? Again, like if the choice of elemental volume is too large, will it be able to take into account the local variation of density? Consider the room that you're right now sitting, for example, then you have switched on your fan and you're trying to measure density of the air that you're living, right? So because of the motion of the fan, there will be some regions of local increase in density and reduction. Of course, that increase in density will be very, very less, because the motion of the air is well within the compressibility limit, but still there will be some density fluctuations. Okay, so if we choose a length scale of that measurement V to be much greater than, to be the length scale of the entire room, so would that make sense? Would that give a proper measurement of density, or should it be something closer to the value of the mean free path of that fluid molecules, air molecules? So what do you think? If you choose the length scale, the volume to be your room, would it take in, of course it will give a result which would be quite close to the actual value, because the compressive effects are negligible, but would it be able to take into account the density, local density variation? Simple question, true or false? Any comments? See, we are in the last minute. Can you suggest? False. Suham says false. So others, can you please comment? The last question for today. Okay, so that's fine. It's fine. Since we are out of time, let me just state the answer. It is false. Okay, so if the length scale with respect to which you're defining the volume for defining the density, if it is too large, then it will not be able to take into account of local variation of density, right, or any other parameter. So that's why you cannot choose this to be elemental volume to be as large as the characteristic length scale of your flow field. So it should be close to the mean free path length. Okay. So yeah, that's all for this week discussion. I hope I was able to clear your doubts, and it was a quite interactive discussion. So let's all meet in the next week, and if you have any doubt, you can put in discussion forum. Yeah. Okay then. Yeah. Thank you. Let's meet in the next week. Okay. Yeah. Thanks, Shanawaz. Let's meet next week. Okay, I'm ending the class. Thanks, Sumit. Yeah. Thanks, Ketan. Okay. Vinod.